Kotler. He's coming from company SafeReach, and here he is.
Excellent. Thank you very much. Thank you very much for coming to my talk today, Backdooring with Metadata. So a little bit about myself, doing security for well over 15 years, presented at different conferences. Check out my website for some of my previous work. There's links to GitHub and other projects, so feel free. So before we can understand why we should backdoor with metadata, I mean, beside the fact that it's cool, let's understand the problem that we're trying to solve and what exactly characterizes or defines our desired solution. So today, we'll talk from the problem perspective that we will talk from will be from what we call a user-land backdoor. So consider the following situation. You're doing a pen test / red team engagement. You pop the box. You're not the administrator. Now it's time to implement the post-exploitation. You want to root or backdoor the box to demonstrate the effect to the customer and prospect. And so you need to basically go ahead and drop something on that machine. And in that process of dropping that user-land backdoor, you may basically compromise the attack because some security solution may kick in at this point. And this is basically the problem that we'll speak about today, and the solution is the backdooring with metadata. So the first failure point in trying to land the user-land backdoor is that transferring it over the wire, networking-wise, could trigger a couple of different security solutions. So if you imagine that we have the My Backdoor executable, so grabbing it, downloading it from an internet site, from the outside network, means going through web gateway or sandboxing that may trigger on it. Laterally within the company, when you will try to pivot to the computer, taking that malware step by step may end up compromising it. And then least but not least, even the mere fact that the computer is connecting with the network, if that's not the profile of that computer, may end up triggering some kind of a security alert. Another aspect that comes into play, again, all part of the problem, is that when you're actually dropping the file into the computer, again, a series of security controllers may kick in and reveal up the operation. So again, saving the My Backdoor into the disk, if it's a known backdoor or malware or whatever tool that you're using for the purpose of that red team and pen test, it may end up having a known bad reputation that again will reveal the operation. And just the fact that you're dropping a new executable may trigger other solutions to investigate, analyze it, and they may come up with a result that this is something malicious, again, blowing up the cover. And running that actual backdoor, now that we're transferring it and dropped it on the box, also has its own limitation, right? Because if that computer, I mean, that backdoor would probably be an unsigned binary, so running it on a computer can yield in two different elements. If there is whitelisting application, whitelisting enable, that simply won't be possible. And even if there isn't, running that again could trigger a security endpoint on that machine, bless you, and basically have that binary analyzed. And again, the result might come positive, saying that this is indeed the malware. So considering these three vital failure points in user-land backdoors, transferring, dropping, and running, and that's without even talking about IT issues. Because yes, pen testers and red teams have IT issues, and the IT issues is just a byproduct of the environment that they operate, right? So there could be connectivity issues trying to get the backdoor. There could be bandwidth issues, stuffing the backdoor into the pipe. And then of course, depending on the environment that you're operating, such as embedded devices, storage may be a constraint as well. And so now that we have defined the realm of the problem, let's see how we can solve it. And we'll begin, of course, with the theory, and then we'll combine it all together into working practical attack vectors. So in order to understand how we can solve it, I'd like to introduce a new concept, and that concept is binaries that could allow arbitrary command execution, and I call that base for short. It's important to understand this is the main ingredient in understanding how you can do backdooring with metadata. And what exactly is backdoors that could allow execution of arbitrary commands? We assume that the purpose of the backdoor is to provide us, to facilitate some kind of needs that we as the attackers has in order to accomplish different tasks. I claim that there is already binaries on a machine, and again, I'll show some demos and reveal some kind of information later on in this presentation. There's already binaries on a machine that are open enough by design or by product, and we'll investigate that too, that can already accommodate those needs. In other words, we do not need to bring anything new to a box in order to actually install a backdoor on it. And again, as we are now introducing into this concept, let's meet our first contendant, find. If you guys ever work with any kind of a Unix or Linux machine, find is a very straightforward utility that basically helps you find files in the file system. Doesn't sound very complicated, sounds very intuitive, and I even throw in some kind of a very simple example, how you can right now search on any Linux or Mac computer for all the files, all your GIF files on the hard drive. That's the command line. Again, very simple, very intuitive, nothing scary over there. However, find also has an interesting option, a flag called -exec. And again, it's not a secret, it's not a mystery, it's out there in the documentation, and it's basically an advanced option that allows find to basically run a command every time it finds a file that matches the search query. So here we can see an example, a very straightforward example, of how I first create a file called foobar in the temp directory. I then initiate the find command, which asks find to find in temp any files called foobar, and then I add the -exec ID, and then there is a certain delimiter that is required to basically help find understand it's the end of the command, and then the result will be that find would actually run the command ID. So let's go from talking about it into seeing it. Okay. So just like we decided, we will create a simple file called foobar, nothing special here, and then we will ask find to find that file, and surely enough, it found it. And then I'm going to add the -exec with the delimiter, and the result is that now it actually executed the ID command. And just to show that it's exactly the same output as I would have entered it into the shell directly. So you may say to yourself, you know, Isaac, it's interesting, it sounds like there is something over here, but what does it really mean? Well, it means that there is already files that by playing with the parameters, and again, this will be part of our following up talk here, you can actually get them to run things that they never intended to do, things that you would like it to do, again, to serve the purpose of that pen testing red team engagement. So this is, like I said, is the vital first ingredient in backdooring with metadata, is understanding which binaries are capable of that capability. Like I said before, there is during the mapping that me and my team has made, we are classified or stumble across two major types. The one is that there is base binaries that could execute arbitrary commands that are doing it by design, and the fine example that I just showed you is one of those. And there's others, which is a byproduct of how they've been developed, or features that the original actor put in the code, but you can then abuse. One way or the other, the first step backdooring with metadata is founding a base, that binary, one or more, on the target OS that you would then like to go ahead and backdoor. The second element in understanding the mechanisms of backdooring metadata has nothing to do with files or has nothing to do with backdooring per se. It has to do with how the Unix kernel is designed, and more importantly, one of the tasks that has been allowed within the kernel, and that's basically to delegate permissions. So every time a person goes on a Linux computer and tries to change the password, running passwd eventually will need to write that password into the main password file. But then again, if the user has an arbitrary right to write into that file, he or she could then just change the root password. In order to overcome this problem and many others, the Unix operation system supports a feature called setuid, which basically means you can separate the privilege of an application from the current user ID who's logged in. In other words, passwd is used setuid to temporarily elevate its permission to the root in order to open the password file and write your password to it, yet it doesn't allow your user to do anything else in the context of the shell. So if this feature existing, it basically means that, and it's applicable, as you will see soon, by simply adding the chmod, which is a binary that's included with almost every Unix distribution. So by basically changing the permission of a file system object, like a binary, and applying the setuid to it, we can now get into a situation where we have a binary that could allow arbitrary code execution, and a setuid option applied on it to elevate it into root. The result is we have an almost perfect backdoor. So taking again the ingredients together and combine them into a one happy big meal, this would be an example of a very simple backdoor using the metadata. Again, the previous example that I demonstrated using find to just find the file and basically run a command. I've changed the command here from just running ID into dropping into a shell. As you can see, the difference in the dash execute from ID is changed now to bash -p. And then it's pretty much remained the same, but the first line of business is that I first chmod that file. I add the +s, the sticky bit, the setuid bit to it, and now it will basically run everything as root. So let's again go into a demo here real quick. So the first thing I need to do is, as root, I need to basically empower the find. And if I'm going back into the example, I'm creating just a file. I'm then asking the file to run. I am changing it from running just ID into running bash. And voila, I just became root. And that's all thanks to chmodding the find that is now running as root, and the capability that was already built in the application to run any command. I simply ask to run a shell, and that shell is now basically a root shell. Again, even if I will remove the setuid from it, it would still work. Technically, there is nothing special that the setuid gave the find except the privilege to run as root. So in this example, now that I remove the setuid bit, I am again dropped into a shell as I requested, but it was the same user ID as I already am, so I've gained basically nothing. So the question that everybody loves to ask when we're presenting exploits and backdoors is, will it scale? So as I said in the beginning, a lot of the ingredients that we're touching here today are ingredients that are part of the distribution and the operation system that is surrounding around Unix and Unix-like OSs. And so me and my team has managed to verify and test the same techniques across different flavors. So you can see there is Debian, Ubuntu, CentOS, FreeBSD, Oracle, Solaris, Fedora, and macOS. And we're not saying that's the end of the list, we're saying that's just the list that we have tested. The idea could be applicable to any operation system that has these two ingredients. Binaries that are having an open-minded in what they can run, and a mechanism to elevate privilege, which is based on a custom kind of a file system permission like chmod plus s provides us with. So it's scaling, yes. So now that we have looked into the problem, we have seen a very short demo of how we can just go ahead and weaponize find to be that backdoor for us. Let's explore a little bit about the different techniques that can reach us into this end state. And starting from the one that we've already explored, the direct command. So during the research, me and my team, we basically start mapping different binaries and look at the different ways that they can accept parameters. And I will show a little bit further into the presentation what are the type of searching techniques that we've used to limit the list, because obviously there's a lot of applications that are coming installed today on these flavors. But we have found a group big enough that we have called it the direct command method. The direct command method is very similar to what we've seen with the find. There are a set of applications out there that by design have capability to run commands. It's part of what they do, and therefore they can be abused with the right elements, with the right setting and schmodding. They can be abused into becoming a backdoor. There are two continuous limitations that I will keep showing up as we're investigating different directions, is that A, not all of them would allow you to pass parameters to. So sometimes they would agree to run a program, but not passing command line arguments to. If you remember from our example, find was nice enough to allow us to add the -p to the bash. It's important because bash by default will drop the privilege. And so supplying that command line is what allows us to basically make it to be a root shell again. Although some can argue that you can use other shells and they won't have that requirement. But then looking forward, in that particular environment, this may be the only viable option. In that case, it's important to remember there's a workaround, which I will then present later in my talk, about how you can outcome. But keep in mind, some of the mappings that you will see would only allow you to run a program without passing a command line into it. And then the other opposite problem that we've encountered, again, this is more for the not by design, but as a byproduct. Sometimes the way that we manage to get a process invocation has, in the context of whatever application that we're exploiting, is designed to accept certain buffers through stdin, or designed to pass specific command line arguments. It's basically forcing that to be as part of the execution context. And that could be problematic, because when you're running a shell, for instance, putting this different information may cause errors or may cause the shell to basically trigger in a wrong way. Again, this kind of an outcome, there's also a workaround for it, but it's important to keep those in mind that as we're playing here with different ways to invoke shells and commands, especially the ones that are not by design, there's going to be weird situation that we should be open-minded to, trying to debug why sometimes things are not working straight out of the gate. So let's see a demo. So again, we already seen a demo of the direct invocation. That's another demo that is worth to mentioning. So there is a program called ANV, which is a very helpful program to create a cross-platform shell scripting. Basically, instead of hard-coding the path to an interpreter like Python or Perl, you can basically call env and pass what kind of environment do you want. If that environment is defined, then the path and the other parameters will be automatically set for. And again, the idea here is that this has been tested on my computer, but on others as well. We're going to chmod plus s, that particular program, and then by wheel, that program passing the bash -p parameter would drop us into a root shell. So again, very simple, very straightforward, and nothing has changed in the process, and we'll touch about it in a second. So it's the same program. We have not changed the file size of env. We have not changed the content of env by any means. MD5s and other hashes, will remain the same. We basically change the file system permission of that program, and that was the outcome. So as I mentioned, the quest to try to map all these different binaries was very challenging because there is no database that we can just go and say, hey, dear database, show me all the programs that by design allow me to run these other applications. Nobody have decided to make it an index or a criteria to be searched for. So the best method that we came with is basically swifting through manual pages that are coming built in the different operation systems and look for keywords that has a high chance that they will then be related to what we're looking for. And so we're basically, this is an example for the keywords of how you can go ahead today on your favorite distribution or Unix-like kernel and basically try to search for binaries and map the binaries that may have this capability. Now again, by the end of this talk, I will release a huge Excel spreadsheet that me and my team has created. However, there's a lot of work that can be done. So I encourage you to do this as an exercise. Learn about your operation system, look for these files, understand what these files can do, and then try to see if you can weaponize them. So, as I mentioned, the pros and cons of backdooring with metadata is the following. Once we do the transformation, once we add the setuid, the sticky bit to it, this doesn't change the file size or content, and so any test that will be based on that criteria will still show thumbs up. Nothing has changed. There is no network or internet connectivity is required in both of the options, find and env. They were already installed on my Mac, and again in many of the popular distribution that you guys are working with today. So we removed that requirement out of our scope. However, there is two disadvantages that we do have to face. First, changing the files of a file could be turned into an indication. So there are certain ways to basically monitor that. So it does create some kind of a noise. And then in this particular method, in the direct invocation method, it will basically be part of the command line. So if you think about tools that presents the command line or what the people are doing in the operation system using something like PS, for example, that could reveal the malicious intention. And again, you can masquerade it, you can play with it, you can be creative with it, but keep in mind, if it's part of the command line, it's something that can be easily looked into and displayed. So the idea that I'm presenting today is not nobly new, and it was actually existed ever since I was a kid and happily reading about hacking in the 80s. And back then, and still is today, the term root shell is designated into what I just presented. So you basically take a file, for instance, you take bash, you copy it to someplace in the system, and you then grant it that particular sticky bit. And so when you think about what's new in my research today compared to the traditional root shell is a very important step. So as you can see from the left side, it's using the BAC, the base method, and on the right side is the traditional root shell backdoor. And both of them eventually require changing the file flags. There is no magic here, but the traditional root shell backdoor basically takes into consideration that you're creating a new file. You are creating the backdoor. And creating that new file creates much more noise than just changing one file's permission. Not to mention that, again, in different environments, embedded device, that could be a limitation. And so understanding the technique today and what's the benefit, we basically avoiding creating file and we only sticking with the metadata, which is in this case changing the settings of the file. And so, fun fact to understand is that the BAC, the base binaries that I'm presenting in today, in some conditions, in certain conditions, can be cross-platform. And this is a very fun fact because it basically means that regardless which CPU architecture you're working with, it can be an ARM or an Intel or AMD, regardless of which operation system flavor you're looking here, the example that I presented previously, the ENV binary, has been verified in all these operation systems. So this is a one binary that you know, that you can just straightly go into it once you pop a box, change the permission of that file, and it will work in all the different flavors, regardless of the specific details or implementation details. That, of course, makes life easier, abstract many things, and basically generate simplicity in the process. ENV is not the only cross-platform. We found a few more. I will say it's rare to find a file that the implementation survives all these different variety, but again, it does happen. We have a few of those, so we can definitely qualify this as a cross-platform idea. The second way to exploit the base, the binaries that could execute a arbitrary command, is if they don't offer the functionality as part of their command line, they may have some kind of customization built into them using environment variables. That was and still is a very popular way to change behavior of binaries by having the binaries reading up specific keys or specific environment variables and acting upon their value. And so a very popular key is the visual editor. So some programs will require you to edit a file, and of course they don't want to implement an editor within the program, but at the same time they don't want to force you, or they can't dictate which editor might be on your system. And so this kind of configuration is left to the environment variables. And so tweaking and playing with the visual and editor is a way to understand that. Again, same limitations applied. So here we can see an interesting case of a program called ViewW, which allows the administrator to change a password. And then changing the password, we can basically declare a new editor to it. However, trying to execute that code as is returns with a failure because it expects a single file and not a command line. And so in order to overcome that problem and overcome other problems that we've talked about here today with binaries that expect certain APIs, we can create a wrapper that will eventually ignore A, stdin, will B, ignore parameters in argv, and always funnel to the same outcome, which is the desired shell. So, like I said, the benefits of using the setuid is to eliminate the noise, create a single funnel to what we would like to establish, which is give us a root shell, and avoid the circumstances. And so the same situation previously, the ViewW here, as you can see, once we took the editor and changed it from the bash p into a temp s, which is just compiling the setuid wrapper and having it pointing to what we want, we have successfully weaponized that particular application as well. Again, a good way to search for application that may be open into that kind of an attack is to basically go for the keywords visual and editor. Of course, there's other keywords that may end up being executable or may end up being useful, but this would, again, for us, yield the majority of the ones that we have found and worked with. So the same advantages as from the other technique, right? No changing of the file, no changing of the size, no internet connection required. However, two disadvantages remains. One, yes, we need to change the file flags, it's given. And B, in some cases where, like we saw the VipW program, we couldn't execute directly our desired command. we had to create a wrapper. That wrapper creation and compilation on the system may end up complicate things sometimes, and therefore it needs to be considered as a disadvantage to this technique. The third method that we have found and we classified is called spawning a process. And the same way that the first category of direct command were binaries that were basically asking them through the command line to run a process for us, in this classification, we have found there is a group of certain binaries that within that program functionality, so if you imagine like a file menu, there is an action item says run a file for me. And this is what we mean by saying we can exploit the function of the application itself to basically launch our root shell. Again, same environment of restrictions. Sometimes running from that context will be limited. Some arguments may be omitted on the way. In other parts, we may be force-fed with different parameters. So the idea of creating a wrapper here is still valid. That wrapper can protect us from the unwanted noise either through stdin or the argv. But the idea here is that, for instance, if we take Python, and there is nothing special about Python, we have found that to be in other programs as well, that basically you can, if you add the setuid, the sticky bit to Python, then you can just simply write a simple program within Python interactive console that would end up creating a root shell. So let's see this in action. So we elevate Python. We are asking Python to, this is weird. This is not the built-in Python. Let's see. No. This is interesting. Well, it must be because of the symlink that I'm not able to actually find the Python file itself. Let's see if I can just copy it for a second here and basically use this and then the symlink. So let's just call this Python here. Of course, it needs to be owned by root for it to be meaningful. Okay. So we have empowered my local instance of Python over here, going and running it. Just to show you that right now I'm a personal user, again running the Python here, asking to elevate the permission of the Python actual interpreter process, and then basically going ahead and asking to pop a shell, and again, I am the root on the machine. And so we have not found many files from this particular category. However, it's still nice to know that it exists, and there is possibilities to abuse programs that has this capability inside. And again, the way to search for that is not very trivial, but the keyword spawn is a good indicator. Same pros and cons. Mainly here, no file needs to be created in the majority of the time. What's important to understand is that now that my talk is near to be finished, I have and my team upload into this GitHub a full mapping, an Excel of all the different files, and I can just show you a little bit of a glimpse of the operation systems that we have mapped. Oh, it's still stuck on the presentation. So just a glimpse of all the different programs that we did. It took a lot of work and a lot of effort, but it's right there, it's up for the grabs. As you can see, there is mapping for Debian, Ubuntu, CentOS. It's free. Go ahead, feel free to take it. We also created a small table for the cross-platform ones that we have found. Again, it's by no way finished or complete. It's just the beginning, but it will give you the right foundation to go ahead and weaponize it in your next pen test or red team. And so this is pretty much the end. We'll just talk a little bit about the mitigation and understanding of how you can find it. So the lesson learned here is know your setuid and setgid binaries. Know them and then check for them. If something changed, you know you have a problem. Normally, these permissions should not be changed unless you installed something new as the administrator or you yourself performed that. And there's also some hardening that you can use, like SE Linux, that basically makes the setuid a little bit more disabled or weaker. But again, it's more complicated. The first one is easier to understand. Future ideas, execution of code is just one thing. You can find binaries that will allow you arbitrary read and write, and then you can chain them together. Just an interesting idea. And of course, other exotic features such as networking. Maybe you can find binaries that do that and use it as part of your backdoor. I'd like to thank my team, and specifically to Itai, who did a great job creating this huge Excel file that is now being shared with you. A lot of hours is spent on trying to test all these different binaries, so I'd like to thank him. And as always, please feel free to reach out to me, to my team, if you have any questions, if you have any comments. Feel free to go to our GitHub, fork it, download it. It's yours. Thank you.